Hello everyone, welcome back to Altium Academy. I'm your host, Zach Peterson. Today, we're gonna be talking about all of the stuff that happens inside the guts of the layer stack manager in Altium Designer. Now, this question came up because of a question on the Altium subreddit, and this relates to what actually happens inside the layer stack manager and how it does its impedance calculations. That's what we're gonna look at in this video. Let's hop into Altium and get started. Now, for those of you that are intimately familiar with the features inside of Altium Designer, you will know that inside the layer stack manager, there is an impedance calculator. And that impedance calculator runs off the back of a Simbeor model, and that is used to give you very accurate impedance calculations. Now, that model is essentially based off of a 3D model provided by Simbeor. Now that's really cool because it basically means that you have a field solver built into Altium Designer, but you don't have to do any of the PhD level math stuff that's needed to configure a field solver tool in order to use it. Unfortunately, for the more inquisitive designer, that means that you don't really know what's going on underneath the surface, and the feature is kind of a black box. Now, I bring that up because it is important for this next question that we have from Reddit. Let's go ahead and take a look. Here, JWaterFlame has posted on the Altium subreddit, impedance matching and defining frequency. JWater writes, in the layer stack manager, you can set your impedance based on numerous things. However, having made a prototype and after lots of debugging, it does start to come down to a mismatching that causes self-resonance. At 50 megahertz, it works with a not so clean signal, but at 200 megahertz, it's failing. Is there an option in the layer stack manager to define the frequency? The thing is, there are multiple communications running on the same plane, not near one another. So is there a way to define the frequency per class or per differential pair so that the calculations are done correctly? So really quick, let's take a look at the layer stack manager inside Altium Designer. Here I've pulled up the layer stack manager for one of the preset 8-layer boards. And if we take a look at the impedance tab, here you can see I've set up an impedance profile for a 50 ohm single-ended line. Now here in the properties panel, if you just kind of scroll up and down, you'll see that there is no option to enter in a frequency value. Now, if you go back here to the Stack Up tab, you'll see here that if I select one of these materials, such as this PP-006 material, that there is an option to enter a frequency in this box. Now, normally this is filled in with 1 gigahertz, and for example, if I select this other core material here in Dielectric 3, you'll see that it is filled in with the default value of 1 gigahertz, and that's the same for these other materials. Now, of course, I can delete this frequency right here, and it's not going to have any impact on the calculation in the impedance calculator. In fact, if I enter in a really high frequency, such as 40 gigahertz, and we go back to the impedance tab and we force it to redo the calculation, you'll see that it returns the exact same trace width. So what this is telling you is that either it doesn't use this frequency value at all, or the calculator has absolutely no dependence on frequency whatsoever. Well, the answer to that question can actually be found inside of the Altium documentation. If you go to the controlled impedance routing article and you scroll down to this selection titled Dielectric Material Behavior, you'll see this text, which I highlighted at the bottom of this section. It tells you right here, all calculations use a default frequency of 1 gigahertz, and if you leave a 0 or a blank entry for the DF value in the layer stack manager, it will assume that the value of DF is 0. So clearly it is using a value of 1 gigahertz somewhere inside the calculation. And what that means is that here for JWaterFlame, most likely his issue is not related to the calculation frequency of the layer stack manager in any way. His issues are at 50 megahertz and 200 megahertz, but the layer stack manager is doing its calculations at 1 gigahertz. Now, I could be wrong about this, and JWaterFlame, if you are watching this video, please hop into the comments section and let us know what's going on with your design, and if you have any insight into the root cause, I'm sure everyone in the community would love to hear about it. But rather than focus on trying to solve a vague design issue without having any of the design data in front of me, what I'd instead like to do is focus on helping you ensure that you get an accurate value out of the layer stack manager while knowing that it is doing the calculation at 1 gigahertz frequency. The first step in doing that is making sure that you have the correct material parameters entered into the materials here inside the stackup. So where can we get accurate DK and DF values to ensure that the impedance calculation is also accurate? Well, you have to get that data from the material vendor, or you have to figure out how to measure it yourself, or you have to extract those values from S-parameter measurements. Now, the second two options that I mentioned are a little more advanced and they're out of the scope of this video. But the material vendors that manufacture these materials do a pretty good job of providing some sort of value or measurement of the dielectric constant at a certain frequency. A lot of times they'll provide that value just at 100 megahertz, or they might provide it at 1 gigahertz. If it's a material that's marketed for much higher channel bandwidths or much higher frequencies, they might provide it at 5 or 10 gigahertz. It really depends on the material vendor. Now, one material manufacturer that does a really great job of reporting all of this data is Isola. And here on screen, I've pulled up one of their DK and DF tables that I have posted on my website. Now, these DK and DF tables contain tabulated data for the DK value and for the loss tangent value for several of their material sets. Now, here I've pulled up the DK DF table for 370HR, which is one of their everyday use materials for me, and I use it in quite a lot of designs. But you can also find DK and DF tables for other Isola materials, and other manufacturers release similar tables that designers can use to figure out what is the optimal DK value to use in an impedance calculator. So here, if you just scroll through these tables, you'll see that they give a lot of data for different laminate constructions and resin content values and material thicknesses. And it's these values that you would want to enter into the layer stack manager in Altium Designer. So here you can see that they give the value at 1 gigahertz, and that's the value that you would want to use for an impedance calculation inside the layer stack manager. Now, if we go back in here to the impedance calculator, of course, if we change this DK value or the DF value, it will impact the impedance that the calculator gives for a given trace width. But if we just scroll through here on the properties panel, you'll see that there's another section here that also depends on a frequency value, and that is the copper roughness. Now, if you've seen any of my other videos about impedance and copper foil and copper roughness and impedance calculations, then you will know that copper roughness does have an impact on the impedance of a trace in a PCB. Basically, when the copper is rougher, that copper will add more impedance onto the characteristic impedance and basically increases the impedance. But the impact to the impedance is also a function of frequency. So just to test out what happens here, what you can do is select one of the standardized models that's built into the properties panel here in the layer stack manager. Let's select modified Hammerstad, which is a really commonly used model. Here, if I enter in a really egregious value, such as, let's say, 4 microns for the surface roughness, I put an appropriate roughness factor, and I ask this tool to calculate what is the impedance. You can see here that for our 9.312 mil trace width, which is what we had earlier, that gives an additional about a half ohm of impedance at 1 gigahertz. But how does copper roughness impact impedance in other frequency ranges, and how do I compensate for that inside of the calculation in the layer stack manager? Well, here I have an article pulled up on the Altium blog. In this article, I've compiled a decent amount of simulation data that shows what happens to the characteristic impedance of a trace at different frequency ranges when there are different levels of roughness in that copper. So here in this graph, we've basically calculated what is the actual impedance for a trace that was sized to a 50 ohm target impedance if there were no losses and no copper roughness and no skin effect in the calculation. So if you ignore all of those factors, you basically have a 50 ohm trace. So clearly, copper roughness has an impact at 1 gigahertz, but what is the impact on impedance in other frequency ranges? And is there a way we can compensate for that inside of this calculation? Well, if you look at any of the standard copper roughness models, you will know that they all have frequency dependence built into them. So there will be an impact on the impedance at different frequencies other than 1 gigahertz. Now, to figure out what exactly that impact is, you need to look at some simulation data. And what I've done here in this article on the Altium website is I've actually calculated what is the true characteristic impedance of a single-ended 50 ohm trace that was intended to be used as a true 50 ohm lossless trace. So basically all of this data shows what happens when we start to add roughness onto that 50 ohm lossless trace. So in this example, we've taken a lossless impedance calculator where the impedance is basically just square root of L over C, and then we've used that to figure out what is the trace width required for that impedance target. Now, once we add in the dielectric loss tangent and we start to add in roughness, you can see that the actual characteristic impedance is larger than the assumed characteristic impedance of 50 ohms. And you can see here that that difference also depends on frequency. So here at 1 gigahertz, you get about a 1 ohm deviation when you have 0 micron roughness, but that deviation starts to increase when you have larger roughness values and eventually getting all the way up to about 1.5 ohms. Now, what about at a different frequency, like for example, 20 gigahertz? Well, if you have a 50 ohm target impedance that's lossless, basically you would be assuming that at 20 gigahertz, your trace is also 50 ohms. But in reality, this data is telling you that when you have 0 micron roughness, so even with perfectly flat copper, your true impedance is about 51.45 ohms. Then once you add in even more roughness, you get up to 0.75 and then 1.5 and then 2 microns, the impedance gets up to 51.7 ohms. So you can see from this data that when we get up to higher and higher frequencies, we have even larger differences between the true impedance and the assumed 50 ohm target impedance. So to compensate for that in the layer stack manager, which is only operating at 1 gigahertz, let's suppose we were operating at 20 gigahertz and we had perfectly flat copper. We would basically want to oversize the trace so that the impedance of that trace was about 1.5 ohms lower than our target value of 50 ohms. So if we're operating at 20 gigahertz, we might want to instead enter in a target impedance of 48.5 ohms. If we do that and then we calculate the trace width, you'll see that our trace width is closer to 10.03 mil, not the 9.3 mil that we had originally. Now, the Altium documentation basically recommends doing the exact same thing with the dielectric constant. You can see here that if a different frequency is required, you pick the DK and DF values from one frequency point from 1 gigahertz to 10 gigahertz from the laminate spec, and then use the characteristic impedance value computed at 1 gigahertz. So basically what they're telling you is that if you need to do a calculation at, for example, 10 gigahertz or 20 gigahertz or any other frequency, you just pick out the laminate manufacturer's data at that frequency and enter it into the layer stack manager. Then the impedance calculator is going to use that value even if that value doesn't exactly correspond to a 1 gigahertz frequency. That's going to give you a reasonably accurate impedance calculation even though the tool is assuming that you're operating at 1 gigahertz. Now, the inaccuracy here doesn't come from the DK value, it actually comes from the DF value. And that is because losses due to the dielectric loss tangent scale linearly with frequency. That also impacts the impedance that would be calculated using a field solver. So let's just suppose that instead of having a DF value of 0.02, I increase it by a factor 5, and I make this 0.1. So if we go back here to the impedance tab and then we ask it to recalculate the impedance, you'll see here that it does change the width required to hit this target 48.5 ohm impedance. Now, it's a very small change because, again, we're operating assumed at 1 gigahertz in this calculation. But in reality, we could be at a much higher frequency, for example, at 20 gigahertz or 30 gigahertz, which means that the impact of DF is a factor 30 larger than at 1 gigahertz. So that's where the potential inaccuracy comes in with a standard laminate. That is overcome or compensated by using a low loss laminate, which is what you would actually do in a practical situation if you're operating at 20 or 30 gigahertz. So to really get a sense for how the layer stack manager and how the impedance calculator operate inside of Altium Designer, you can always open up a blank PCB, load one of the preset stackups, and just start playing around with the parameters. After you start playing around with the dielectric parameters and the roughness parameters and the geometry, you'll pretty quickly start to see how impedance is impacted as you change all of those parameters in the stackup. Thanks everyone for watching this video, and thank you to everyone that's active on the Altium subreddit. As we see more great questions come through the Altium subreddit, I'll make sure to put them here on the Altium Academy channel. Make sure to hit that like button, hit the subscribe button, leave your comments and questions in the comment section, and last but not least, don't forget to call your fabricator, folks. We'll see you next time.